In this video, we're going to be discussing concavity of a cubic function. Okay, perfect. So, ladies and gents, we are given that I'm just going to write it as f of x. Ne? So we're given f of x equals to minus 2x cubed plus 4x squared minus x plus 1. That is the equation of the function. For us to do concavity, we need the second derivative test, right? So I'm going to do the first derivative, which is minus 6x squared plus 8x minus 1. That one becomes 0. This is the first derivative, right? And then let's do the second derivative. The second derivative will be minus 12x plus 8. Right. Perfect. So we have all the information we need. So remember, f of x is a representation of the graph itself, right? The y values on the graph. And then f prime x, or the first derivative of f, just represent the gradient, right? The gradient. It's a representation of the gradient of the graph at any x value in the Cartesian plane. Perfect. And then the second derivative tells us about concavity, basically. Ne? Perfect. So the first most important thing we need is this. We need point of inflection. Point of inflection. Then I'm going to quickly show you how to calculate this point of inflection. So what you do is you take your second derivative. So the second derivative of f of x must be equals to 0 for point of inflection. Point of inflection is where concavity changes, basically. Ne? Concavity changes here on the point of inflection. Sharp. So let's see. Second derivative, we said it's minus 12x plus 8, which will be equals to 0. And then we are going to have minus 12x equals to negative 8, divided both sides by minus 12. And then we have x equals to, let's see, minus 8 minus 12, which is, we're getting 0.67. I'm going to round off to 2 decimal places in this case. But the actual value is basically 2/3. Sure. So that is my x value on the point of inflection. I can show you the other way to do. We could have done it if we didn't want to use the second derivative. We could have said this. The x value on the point of inflection, it's always halfway through these x values. So you take the biggest x value, which is 194. Or they were doing 3 decimal place. Let me also do 3 then. 667. Sharp. And then you minus the smallest x value. So this is the biggest x value on the turning point. You take the smallest x value on the turning point, which is 0.14. And that gives you the distance. But remember, I said it's halfway. So you divide that by 2. Let's press that on a calculator and see. So it's 1,194 minus 0,14 all over 2. That gives me a different answer. Let's see why. $1.194. Should I add on? Let's see. The sun. So I advise you to always leave it in this form. S 2/3. Unless you are doing a sketch, then you can approximate it in this way. Okay, the reason, ladies and gents, I switched to 3 decimal places is because I saw that that one there is 3 decimal places. So I used 3 decimal places there. So now let's see. We are going to do this now. Let's see. I'm going to show you another way to get the point of inflection at x value. So x value on the point of inflection is the sum of the x values on the turning point. So the first x value is 1.94. The second x value is 0.14. So plus 0.14. And then you divide it by 2 is the average basically. So let's see, what does that give us? 1.194 plus 0.14. And then that we divide by 2. It gives, if you were pressing with me on the calculator, you can see that it gives you 0.667. Right. And then that is the x value where the concavity is going to change, which is somewhere there, right? When I approximate it, it should be somewhere there, which is basically 0.6, I can say 67 if I round off to 2 decimal places. Let's get the y value. So we are going to substitute 0.67 here, 0.67 there, and then 0.67 there, 0.67 there. Let's do that. So I have negative 2, 0.67 cubed plus 4 open bracket, 0.67 squared minus 0.67 plus 1. That gives us 1.524. So the answer will be equals to 1.524. So the y value on the point of inflection is 1.524. Or you can just say 1.52, right? Can show you another way to do it. The y value on the point of inflection is the midpoint of the y values. So the first y value on the turning point is, you only work with the turning points. You don't take any x value. It's the midpoint of, basically point of inflection is the midpoint of the turning points. Sharp. Think of it that way. So 2.104 plus 0.933 all over 2. Let's see, what does that give us? So we have on a calculator 2.104 plus 0.933 all over 2. That gives us, if you are pressing with me, it gives you 1.52. Do you see it? So the easier way to do it, if you have the turning points, you can just do the midpoints. That will give you the point of inflection. But it is very important to know that it's the second derivative of the function, where the second derivative is equals to 0. Okay, sure. So guys, point of inflection, I said, is where the concavity changes, which means it divides our graphs into 2 parts. Into this part, you can see that here the graph is concave up. You can see that here it's concave up because the graph is up there. And then you can see that this side from the point of inflection going there, it's what? It's concave down, you see? Because it's facing down. Perfect. We can prove it that indeed by, okay, let me start with this. We can say, okay, for concavity, right? Let's make space and go up a little bit. Sharp. We can say, okay, for concave up, right? X must be less than this because to the left we are concave up, you see? So we are saying X must be less than 0.67. Do you get it? Perfect. And then for concave down is just the opposite. Concave down, x, you can see it's going to be this side. It's going to be x is bigger than 0.67. Okay, so in simple terms, for concave up, the x value must be bigger than the x value on the point of inflection. And for concave down, the x value must be smaller than the x value on the point of inflection. And you know how to get the point of inflection. So we can do this then. We can say, okay, with this finding here, we can basically say, okay, for concave up, we know that the second derivative must be what? The second derivative, remember concave up, guys, the second derivative must be bigger than 0. Ne? Sharp. Now let's prove that we're going to get the same answer. For concave up, the formula is this. Now you need to know it. This is the formula for concave up. Let's prove if this is true. So we have minus 12x plus 8 is greater than 0. You have minus 12x is greater than minus 8. And then you're going to divide both sides by negative 12. So let's divide by negative 12 divided by negative 12. Remember, the inequality sign switches. So you have x is less than 2 over 3, which means x is less than 0.67. And that proves that. Ne? So for concave down, we are going to do the same, but now the second derivative must be less than 0. So these are the two most important formulas. Ne? This is the first one. That is the second one. Concave up, you make the second derivative bigger than 0. Concave down, you make the second derivative less than 0. Right, ladies and gentlemen. Perfect. And then I'm sure you can see that, okay, I want to show another trick here. Ne? Let me show you something. Let's say you are looking at this x value. Ne? Let's say you don't have the graph. You're looking at this x value. You're like, okay, this x value, right, it's on the left of, it's on the right of this one. And from this one going to the right, we have concave up. It means you are like this. Concave, so here we are on the right of this one. So we are concave down. So we are facing like this, you see? Because this 1.194, it's bigger than this one. So we're facing down. It means that x value is basically your turning point. And that turning point, we're going to call it local maximum because we are facing down. We are concave down. It means we have the highest point. And so too, you can do the same with this one. Ne? For concave up, you know that your graph is facing up. So you're going to have a what? You're going to have a minimum value or local minimum. Ne? Sharp. So how do you know that your local minimum is going to be here? By just looking at this. You know that, okay, any x value that is smaller than this will be on the concave upside. So, and also on the turning point, we are on the concave upside. You see it? Because this is smaller than that. So any x value that is smaller than this. So xtp, remember, is equals to 0.14. So it's smaller than this one. So it means it's on concave up. So concave up, it means we are going down. We are going down, then up. You see? Down, then up. Sharps, like our curve is facing up. So that will be the smallest. So that is the local minimum. But that is too advanced when you understand it properly. Keep on watching these videos and we'll get more into first derivative test and second derivative tests. But the most part of this video is you need to know how to get the point of inflection, and you need to tell us the x value when it's concave up, and you need to tell us the x value when it's concave down. Thank you very much. Thank you.